Pressure changes also have a big effect on our weather. Variation in atmospheric pressure creates wind, and changes in the pressure help us to predict the weather. So that's, a whole nother area of science, meteorology. But they can look at low pressure systems and high pressure systems, and that helps them to predict what the weather's going to do. Now, it's not an absolute, but it's a lot better than just guessing. High pressure usually is associated with nice weather, and low pressure with unstable weather. In the atmosphere, the number of gas particles in a given volume, you could say the concentration, decreases as you go up in altitude. And so the pressure also decreases with increasing altitude. So here we have a picture showing those look like mason jars, don't they? Could be more scientific. 2 mason jars with gases in them, nice pink gas. I don't know what that would be. This gas has fewer particles. This jar has fewer particles than this one does. So this has a lower pressure than that one. The volumes are the same. The jars are identical. This one has a higher density as well, because the mass of this in the same volume is larger than the mass of this one. So fewer particles means lower force per unit area, lower pressure, lower density. Our ears are sensitive to differences in pressure, and you've probably experienced this if you've ever flown in an airplane or gone up to see the big trees at Grant Grove. When you go up the mountain, the atmospheric pressure decreases. The air is less concentrated. We say it's thin, right? It gets harder to breathe when you get up there. And you also get this sensation in your ear. So inside your ear, there is it's just your eardrum. Sorry, I just blanked on the name of that. You have your eardrum. So it's this membrane that separates your outer ear from your inner ear. And there is air present inside your head and air on the outside. And so when the pressure is reduced outside, the pressure inside is still normal pressure, and it causes your eardrum to bulge outward. And that can be uncomfortable, especially if you have an ear infection. And so what happens as you go up? You yawn, you chew gum or something, and you have this popping sensation, right? And then your ears feel better. The popping sensation is when the eustachian tube, which goes down into your throat, releases the pressure that is in your inner ear. And then your eardrum isn't bulging anymore, and things are good. Didn't know this. This is as close to biology as we're going to get. And then when you come back down the mountain, you get that uncomfortable feeling again, and your ears need to pop again. That's because your inner ear was at the same pressure as the air up in the mountains, and as you come down and the outside pressure increases, now your eardrum's going to bulge the other way, also uncomfortable. And you need to get it to pop. That's how we identify that feeling, getting this tube to open up and let air back in to equalize the pressure. If you have a cold or any allergies or swelling, then it's more difficult for that to happen, and it can be extremely uncomfortable. This is the reason that babies cry on airplanes. They have very tiny eustachian tubes, and so it's very difficult for their ears to pop. The plane is pressurized, but it's not pressurized at the same pressure as it is down below, and so your ears need to pop for you to be comfortable, and babies have a hard time with that. When you chew gum, when you swallow, when you yawn, things like that, that helps that eustachian tube to open up. Any questions about that? I like how science can explain stuff that we actually experience, right? I'm not going to test you on that, but just want to make sure everybody knows about it. That would be a funny test question. Yeah, why does your ear pop? Explain that to me. But now you're going to explain it to your friends. So how do we measure pressure? Well, probably the original way of measuring atmospheric pressure is a Mercury Barometer. And this was a very, very simple device. It involves a dish of mercury. Mercury is a metal, but it's a liquid at room temperature. It's really, really neat stuff, but it's also toxic, so we don't get to play with it. You take a long glass tube full of mercury and you invert it in this dish of mercury. Now, if you did this with water, and you could do this in the sink or in the bathtub, and you've got some water here, and you put a cup underneath, and then you pull the cup up, and the water just stays in the cup. And you can play with that, and then you lift it up out of the water, and then all the water comes out as soon as this edge of the cup leaves the surface of the water. It's something that kids do in the bathtub. What happens here is the mercury is much more dense than the water, and so some of it will actually come out, but not all of it. And here's a question: why does the water stay up inside the glass? We know that it does, but why? It's atmospheric pressure. It's the pressure of the atmosphere. So what we've got going on here is atmospheric pressure is pushing down on everything. It's pushing on you. We don't feel it because it's always there. It's like your socks, right? You put your socks on, and at first you can feel them, but then later in the day, you're like, I don't know if I'm wearing socks. Now you all feel your socks because I pointed it out to you. The atmospheric pressure is pressing down. The mercury or the water wants to come out of this tube because gravity's pulling on it. So we have opposite forces here, because for this mercury to come out, this liquid here, the liquid mercury, has to rise up, which opposes the force of gravity. Opposes the atmospheric pressure. So the atmospheric pressure is trying to keep this level constant. Gravity is trying to bring this down. And so at some point they are in balance with each other, and that happens when the column of mercury is 760 millimeters tall. It's about 29.92 inches. With water, that distance is much larger. It's more like 32 feet. And so that's why the water stays in your cup. It's not dense enough. "29 inches is actually quite long. So it's from the end of this meter stick to about where my thumb is. So a column of mercury that tall can be supported by normal atmospheric pressure. If the atmospheric pressure decreases, then the height of the column of mercury also decreases. If this pressure increases, the mercury goes up in the tube. And so here we've got a couple pieces of glassware, a bunch of mercury, and all we need is a ruler, and we can measure the pressure. So the original unit for atmospheric pressure was millimeters of mercury, because literally you're measuring how tall the column of mercury is. So that's abbreviated MM, capital HG. Higher pressure, higher column of mercury. That has been given a fancier name. It's also called a torr, after Torricelli, who's the guy who came up with this barometer. A torr and a millimeter of mercury are exactly the same thing. They're two different names for exactly the same thing. There are other units as well, and the reason we have so many units, besides people liking to have their own thing, is that they're useful in different situations. So the SI unit is the Pascal. Pounds per square inch is what you look at when you're inflating your bike tires, your car tires. Here's the torr. Inches of mercury is what the meteorologists use, and atmospheres. So an atmosphere is normal atmospheric pressure at sea level. We have this little weather station in the classroom. It says 29.70. That's inches of mercury. That's the current atmospheric pressure in our classroom. It's very close to 29.92 because we're only about 300 feet above sea level. But that will go up and down with the weather. So this is actually a conversion chart, a table of relationships. The way this is set up, these are all equal to each other. So all of these things are equal to 1 atmosphere. So 14.7 psi is equal to 101,325 pascals. The only exact conversion here is that 760 torr, or 760 millimeters of mercury, is exactly equal to 1 atmosphere. The rest of them are not exact. So converting with pressure units, just dimensional analysis. The beauty is, though, it's always one step because of how we're given the conversions. So the local weather report announces that the barometric pressure is 30.44 inches of mercury. It looks like in mercury, but it's inches. Convert this pressure to PSI. This is the sort of table or information I'll give you on an exam. I think it's helpful to remember that an atmosphere is 760 torr, which is 760 millimeters of mercury, because we use that a lot, but I'll give you these conversions for an exam. So we're given 30.44 inches of mercury, and we're asked to find PSI, pounds per square inch. I can do this in one step. I'm going to put PSI on top, inches of mercury on the bottom. Just looking at the units, how are the units going to cancel out and give me what I want? Okay. I can get the relationship between any two pressure units from this. So here I have PSI, inches of mercury. There's my inches of mercury. This is my PSI. So 14.7 PSI is 29.92 inches of mercury. 30.44 times 14.7 divided by 29.92. The 14.7 is not exact. It's actually just 3 sig figs, so then my answer should have 3. And then when I round, this is the digit I'm getting rid of, so I need to round my 9 up to a 10, which rounds the 4 up to a 5, but I still need 3 sig figs. Better looking 0. So that's equivalent to 15 PSI. Any questions? Yeah, it's just like molar masses or any of the other unit conversions. You just put the unit that you want on the top and the unit that you are given on the bottom. You find the appropriate numbers and stick them in. The nice thing is you never have to go through a whole bunch of different things. Inches to feet to yards to miles to stuff like that. So a barometer measures atmospheric pressure. Sometimes we want to measure the pressure of a container, like maybe your tire, right? You want to measure the pressure. Well, we have modern pressure gauges, but the old-fashioned, easy-to-understand one is called a manometer. Which, makes you think that it's measuring man, but it's not. It's measuring the pressure of a gas. So this is essentially a barometer hooked up to a container. So here we have a U-tube, a U-shaped tube, partially filled with liquid mercury. It could be done with other liquids as well, but this one's mercury. So here I've got a container with gas in it, and this is under pressure. This gas is going to try to escape, and so it's pushing down on this column of mercury. The atmosphere is also pushing down on the mercury. And so what we see here is that the gas in the container is winning. right? It's pushing down further on this side than atmospheric pressure. Because what would this look like if we had it open to both sides? We had a tube here, and it was open on both sides. If the level was here on one side, where would it be on the other side? Same, right? Because gravity's pulling it down, and the atmospheric pressure is the same on both sides. If you took that tube, and you wouldn't want to do this with mercury, but maybe you had liquid in a, like juice or something, in a bendy straw, and you push down, you blow on one side, then the other side's going to go up, right? Because you're putting pressure on this side. Does that make sense? So we're seeing that the gas in here is pushing down on the mercury, causing it to go up on the other side. So what this does is it tells us the difference in pressure between atmospheric pressure and what's in the container. And we can measure that with a ruler again. We can measure that in millimeters of mercury. Any questions?